This is the second section of the proof by induction chapter, proving divisibility results, and we have 4 steps to prove divisibility. There is one slight difference though. So let's say, for example, and this is going to be the first example that we do in a moment, let's say that I needed to prove, and this is going to be by induction, that 3 to the power 2n plus 11, or plus 11 like this, not as the power. So in a moment you'll see this is our first example, is divisible by 4. So it is divisible by 4. So the first thing we do that's different to the previous one is, before we even start the basis step, we say let f of n equal that statement that we've been given. So in this example here, I would start by saying let f of n equal, and I'd write this statement like this. So that's step number 1. That's slightly different to what we did before. So in our basis step, when we're trying to show that it's true for n equals 1, we actually want to show that f of 1 is divisible by whatever value it is. Okay. The next thing we do after that is we then assume that f of k is divisible by whatever value that happens to be. Then in the step after that, where we're actually going to be writing out f of k plus 1, we actually do f of k plus 1 minus f of k. Now the reason we do this is because if we assume that this is divisible by a certain amount, so divisible by whatever, then f of k plus 1 minus f of k, yeah, should also be divisible by that. Now if that is, that's our proof by induction. Yeah, so we let f of n equal the statement, we prove the statement is true for f of 1, we then assume it's true for f of k, we then work out f of k plus 1 minus f of k, and we should have a statement which is divisible by the number we're looking for. And the statement that we have should contain, not always, but it often contains f of k. You'll see that in the examples that we do. So here in proof by induction that for all positive integers, 3 to the power 2n plus 11 is divisible by 4. So step number 1, set this equal to f of n. So you could say let f of n equal 3 to the power 2n plus 11. So that's before we even start our basis step. So the basis step is going to be working at f of 1. It's going to be 3 to the power 2 times 1, or 3 to the power 2 plus 11. So that's going to be 9 plus 11, which is 20. Okay, so in our basis step, we've shown that f of 1 is divisible by 4. And if you want, you could write down that 20 is 5 times 4. So it's a multiple of 4. It's divisible by 4. Then we're on to our next step, the assumption step. And in the assumption step, we're going to assume that this statement is true for n equals k. So we actually now write down f of k equals 2 to the power 2k plus 11. The next step is our induction step, or inductive step. So I'll write down induction, or I could write inductive, doesn't really matter. So now we set f of k plus 1 is going to equal 3 to the power 2, and n gets replaced with k plus 1, like this, plus 11. And then the step that we use for divisibility is that we're going to do this, and we're going to subtract f of k. Yeah, so after this, what we now do is f of k plus 1 minus f of k, and we want to show, is this divisible by 4? So that'll be 3 squared, and that power gets times by k plus 1 plus 11, so that's f of k plus 1, and we're subtracting f of k, which is 3 to the 2k plus 11. So the rest of this now is trying to get out 4 as a factor. So I can see that actually I've got plus 11 minus 11 there, so that's gone. So let's just write down what's left. So we've got 3 to the power 2 k plus 1 minus 3 to the 2k. So next thing I'm going to do is to multiply out that power. So I'll have 3 to the 2k plus 2 minus 3 to the 2k. So the first term can be written as 3 squared times by 3 to the 2k minus 3 to the 2k. So 3 squared is 9. So I've got 9 lots of 3 to the 2k. Take away 1 lot of 3 to the 2k, which leaves me with 8 lots of 3 to the 2k, and 8 is 4 times 2, so I've got 4 times 2 times 3 to the 2k. Okay, so therefore f of k plus 1 minus f of k is divisible by 4 on the assumption f of k is divisible by 4. So we can say something like, hence by mathematical induction, 3 to the 2n plus 11 is divisible by 4. Done. So different type here, same method, prove by induction that for all positive integers n, n cubed minus 7 and plus 7, plus 9, sorry, is divisible by 3. So step number 1, let f of n equal n cubed minus 7n plus 9. Step number 2, which is our basis step. So we don't really need to write down the word basis. We can just say f of 1 equals 1 cubed minus 7 times 1 plus 9. That's going to be 1 minus 7 plus 9. And that gives you 3. So then we can say, therefore, when n is 1, the statement is divisible by 3. Is divisible by 3. Okay. Next step is our assumption. So again, we don't need to write the word assumption. We can just write something like assume f of k, which is going to be k cubed minus 7k plus 9, is divisible by 3. This, if we write this as we go along, it saves us writing a huge long conclusion at the end, because we're writing our conclusions as we go along. So we assume f of k is divisible by 3. Therefore, we can say f of k plus 1 minus f of k equals, so that's going to be k plus 1 cubed minus 7 times k plus 1 plus 9 minus, so we just put k in, k cubed minus 7k plus 9. So now we multiply out the brackets. Now the k cubed part, this here, we can use the binomial expansion, so that will just save time, so we can work out what the coefficients are. 1, 3, 3, 1. So that will give us a k cubed. So this is just for the k plus 1 all cubed. So k cubed, then plus 3 lots of k squared, plus 3 lots of k, plus 1. Yeah, that's the quick way of doing it. Then we'll multiply the other bit. So minus 7k minus 7 plus 9. Then in the second bracket, well, there's nothing to multiply out, but we'll just write it down. K cubed minus 7k plus 9. So now we'll simplify it. So you've got k cubed minus k cubed, so it's gone. We've got 3k squared, so let me maybe cross these out. So that's gone with that. We've written down the 3k squared. Then you've got 3k minus 7k. And then you're going to have a plus 7k, so these cancel out here because you've got the minus there. So that just leaves 3k, so plus 3k. And then in terms of the numbers, well, these numbers are going to cancel out because you've got 9 there, minus 9, so that's gone. So that just leaves plus 1 minus 7, which is going to be negative 6. Negative 6. And we can factorize out 3 like this, plus k minus 2. Okay, so here we go. There's 3 times something, so it means we can just write down, so f of k plus 1 minus f of k is divisible by 3. So we can just write something down like this. Therefore, by mathematical induction, n cubed minus 7n plus 9 is divisible by 3, 4, and then we can add this. I didn't add it on the last one, but we can add this, that it's true for all positive integers n. Another one here. So I want to prove that this statement for all positive integers is divisible by 133. Right. So start off f of 1, our base, well, before our basis step, sorry, f of n is 11n to the 11 and then the power is n plus 1 plus 12, and the power is 2n minus 1. So in our basis step, we do f of 1. So it's 11 to the power 1 plus 1 plus 12 to the power 2 times 1 minus 1. Now I know we could do these in our head, but it's always best to write it out fully, because you'd be surprised you can make some really basic silly errors in an assessment if you're not careful. So that will be 11 squared plus 12 to the power 2 times 1 is 2 minus 1. See, look, I had to think about that. Now if we work that out and we do 11 squared plus 12, now I know 11 squared is 121, plus 12, That's 133. Okay, so we can say therefore, you can do 3 dots, that means the same as it. Therefore, f of 1 is, or when n is 1, therefore when n equals 1, the statement is divisible by 133. So each one of these questions, I'm just using slightly different wording, variations on the wording. You know, you have choices as long as you're clear about your steps and what you're doing. So we're now on to the next step where we're going to assume f of k, which will equal 11 to the power k plus 1 plus 12 to the power 2k minus 1 is divisible by 133. So the next step would be so we can use therefore. We're now going to work out what this f of k plus 1 minus f of k. We're going to show if this is divisible by 133. So f of k plus 1 will be 11 to the power k plus 1 plus 1. So write it out fully. Plus 12 to the power 2. That'll be k plus 1 minus 1. Minus, so we're now going to subtract f of k like this. I want to put the brackets in here. Right, so on this one, there's lots of ways we could proceed. We could like try and multiply them out or something like that. But I'm going to start like this. Let me just move this minus sign over here, like that. And I'm actually going to factorize it without really multiplying everything out. Yeah, and you'll see the technique that we're going to use. So for example, I can see that in the first two terms, so in this term here and this term here, there's a common factor of 11k plus 1. Okay, so I've got 11k plus 1, which I can take out as a factor. So in the brackets, I would have 11, yeah, because that plus 1 is like times in by 11 from the first term, and then the first term in the second brackets, I've basically got one of those, so I'll take away 1. Now I'm going to do the same thing in the second bracket, and I'm going to take out the lowest power as a factor, which is going to be 12 to the power 2k minus 1 as a factor. Now for that to balance and work with this power here, which when we multiply it out will give us 12 to the power 2k, and then we'll have plus 2 minus 1 plus 1. Then that 12 to the 2k minus 1 needs to be times by 12 squared. You need to add 2 to the power basically. Yeah, so 12 squared there, and then what have we got? We've got one of them in the second bracket like that. So this becomes 10 lots of 11k, or 11 to the power k plus 1 there, and then plus, now we've got basically 144 minus 1, which is 143, times 12 to the power 2k minus 1. Now you may notice that we've got a 10 here and a 143 here, and 10 minus 143 is 133. We could say, right, having 143 lots of something is the same as having 133 lots of 12 to the 2k minus 1 and another 10 lots of 12 to the 2k minus 1. So what we'll do, let's take out 10 out as a factor. So when I do that, I'll have 10 lots of 11k plus 1 plus 10 lots of 12 to the 2k minus 1 plus 103 lots of 12 to the 2k minus 1. Now have a look at this bit here. Recognize that? That is the assumption that we made in the previous step. So this is the same as 10 lots of f of k plus 133 lots of 12 to the 2k minus 1. Now we assumed that this bit was divisible by 133. Now if we assume that bit is divisible by 133, then the next bit here should be divisible by 133 because you've got 133 lots of something. Yeah, so because of our assumption, we've now got a statement here where we can say so f of k plus 1 minus f of k is also divisible by 133. Therefore, by mathematical induction, because we've said all our bits as we've gone along, so we don't need like a huge essay at the end. By mathematical induction, 11 to the power n plus 1 plus 12 to the power 2n minus 1 is divisible by 133 for n when it's any positive integer. So you should now do exercise 8b on page 162. So just a recap for this proof of divisibility. So step number 1 is going to be to let f of n equal our statement. Step number 2 is to show that f of 1 is divisible, and then state that that when you have 1 it's divisible. Then you write your statement equal to f of k. So you replace in your statement any n's with k, so I suppose it should be that, shouldn't it? Then we now do f of k plus 1 minus f of k, and then we need to show that that expression that we get is divisible by whatever we're proving it's divisible by, and then at our n at the end just write our conclusion. And hopefully we've proved by induction that a certain statement is divisible by a particular number.